A spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks from the spotlight towards the building at a speed of 1.5 meters per second, how fast is the length of his shadow on the building decreasing when he is 4 meters from the building? Let's get a little bit of a diagram to look at what's going on here. Okay, here we have a very bad drawing. I have not and probably will never be a good artist, so you're just going to have to put up with that. We've got this little spotlight here, and we've got the building here, and the person walking in between, and the spotlight shines and hits that man's head and continues. And so all of this over here is basically what's in the shade, basically the shadow. And of course, this man is moving, and so what's going to happen is this triangle is going to change depending on where he is, but this is a general drawing of what happens. It's just the quantities are going to end up changing. So let's see what information we actually have. So a spotlight on the ground shines on a wall 12 meters away. So we know that this whole distance is going to be 12 meters. Everything's in meters, so we'll just write 12 there. And then the man is 2 meters tall. So this dude here is 2. And he is walking away from the spotlight. So we don't know how far he is from the spotlight. That is an unknown. I'm going to write that as x because we often use x to represent horizontal distance. That means that this unknown over here is going to be 12 minus x. Because if that whole distance is 12 and one part is x, that means the remaining bit is 12 minus x. We could have decided that this was going to be x and that was going to be 12 minus x. But I think the math is going to be a little bit easier if we let this be x right here. And then the height is also going to be something that changes, because if that man is closer to the wall, then the angle is different and we've got a shorter shadow. So I'm going to call that y. And now we have everything labeled, and we need to figure out rates of change. So the thing that we're looking for is how fast is the length of his shadow decreasing. So the shadow is y, and we want to know the rate of change there. So we want dy over dt. And the rate that we're given is that he is walking from the spotlight towards the building at a speed of 1.5 meters per second. So we have the rate of change of x. We have dx over dt. So what we're going to want is a relationship that relates x and y that we can differentiate implicitly to get a relationship between dx and dy. So we need a relationship here, and we've got a diagram with a whole bunch of things in it. We're not going to use the Pythagorean theorem because we don't have any use for the hypotenuse of this big triangle or even the smaller one, but we do have actually two triangles, and there's a relationship between those two triangles. They're both right triangles, and they both share this angle down here. They're actually both similar triangles. Those are triangles that have the same angles. And there is something that's true when we have similar triangles. If we look at the ratios of the sides are in proportion to each other. So if we look at the ratios of the bases, the shorter base is x and the longer base is 12. So we can write x over 12 equals, and then we can look at the heights and relate them. The shorter height is 2 and the longer height is y. So that's going to be 2 over y. And so that is the relationship between x and y. We could also, if we wanted to cross multiply here, we could take x times y equals 12 times 2, So we could write this as xy equals 24. Either one of these is a relationship that we can use, and we can choose either of those to differentiate implicitly. I would like to avoid having to deal with the y in the denominator. So I'm actually going to differentiate this one, but either one of these should give us the same answer. So let's differentiate this one on the right with respect to time. So d over dt of xy equals d over dt of 24. We're going to have to use the product rule here. So when we take the derivative of that, we've got the derivative of the first, which is going to be dx over dt, times the second, which is y, plus the derivative of the second, which is dy over dt times the first, which is x, and that equals 0 because the derivative of a constant is 0. Okay. And then we need to figure out what we can plug in. Now, the moment that we're looking at is the moment when this person is 4 meters from the building. So at this particular moment, I'm just going to draw a very, very crude version of this. We know that at this moment, he is 4 meters from the building. The whole base is still 12. That means that x is actually 8. He's 8 meters away from the spotlight, and then he's still 2 meters tall, and we don't know what y is, but we know in this case that x is 8, so we can actually plug that in and figure out what y is. We can plug it into either one of these equations. Let's actually use this one. That looks a little bit simpler. We know that in this moment, x is 8, and 8 times what is 24? 8 times 3 is 24. So we know that the value of y is 3 at this moment, and we can start plugging those things in. So y is 3, and x is 8 at this point. And we have dx over dt. We know that he is walking towards the building at a speed of 1.5 meters per second. So x is changing at 1.5 meters per second. So dx over dt is 1.5. We do not know dy over dt yet. That is our unknown. So we need to solve 1.5 times 3 is actually 4.5. And we want to get that to the other side by subtracting it. So this is going to give us dy over dt times 8 is negative 4.5. And to get dy over dt alone, we divide both sides by 8. So that's negative 4.5 over 8. And when we divide that, we get negative 0.5625. And this is a speed here, and so it's going to be measured in meters per second. And so the question we were asked, how fast is the length of the shadow on the building decreasing? It is decreasing at a rate of 0.5625 meters per second.